Did I put the solutions up there? They're not there? Well, we can go through this one very quickly. And the reason I'm saying this is because this was meant to be a very trivial quiz. It was not meant to be in any way, shape, or form hard. Just that if you're acquainted with the homework, this should have been an automatic. However, if you try cramming, and I warn you about this continually, if you don't do the homework after every class period, what happens is you cram a lot of information in one day, and you will get confused and forget it. It's best to take so much information per day and just reinforce it the night before a quiz. Don't try to cram it, because it's really gonna hurt you in the long run. You'll forget it. And the final in here is comprehensive. And remember one other thing, all the things you're learning are things that they're gonna assume you know when you go to the next EMAG, and also other classes, senior level classes. And so just keep that in mind. Cramming is a good way to really hurt yourself. Keep that in mind. All right, now for this quiz, what I really had is two charge distributions. I had one at 1 meter, and this is X, Y, and Z, correct? And this I'll just call Q2, and it was minus, I forgot, minus what, 2 nanocoulombs?
Minus 5 nanocoulombs.
5 nanocoulombs. And then I had a line charge, an infinite line charge, with a charge density, rho L here equal to, is it 2? Plus 2 nanocoulombs per meter. All right, now that's a line charge, and it's at minus 1, y equals minus 1. So first thing you might as well start getting used to doing is just write out what the equations are in the general form for each of these. For a line charge, we know that the E field from the line charge is equal to rho L over 2 pi epsilon naught rho in the A rho direction. Now rho is a vector going from, it's a perpendicular vector drawn from the center of that line charge to the point of observation of the electric field. And the electric field was up here at a height of what? Class?
2 meters.
Z equals 2 meters. So really, this is Z equals 2 meters here. Rho L is given epsilon naught I gave you. Rho, vector rho, is always the position of the point of observation minus the coordinates of the actual center of the line charge, correct class? So if we do that, we get really, well, the distance, the actual distance in X is irrelevant because the line charge is infinite in the X direction, correct? So the next one is Y, if we're gonna stay in Cartesian coordinates. Well, the Y coordinate of this point is 0, minus a minus 1 is 1, AY. And then when we look at the Z coordinate difference, the coordinates of the point of observation is 2. So it's going to be 2 minus the Z coordinate of this line charge is 0, or just 2 AZ. So that's A rho, correct class? Now when we get a unit vector, A rho, that's rho vector over magnitude of rho. A lot of people miss this part. Do you agree with me? Y'all say this right now? This is important. I think a lot of people didn't spend time on this because I made sure I gave you several homeworks and talked about this in class related to this. Here, that's going to be equal to AY plus 2AZ over square root of 1 squared plus 2 squared is square root of 5. Correct, class? Therefore, I have really all the information I need for this. So when I go to the next one, when I talk about, let's see if I get a better marker here.
I guess so.
Well, let me try these first. I appreciate it. We'll use this one. When we actually do the point charge, we know that E from the point charge is equal to really Q over 4 pi epsilon naught, and then that's R, doesn't matter if it's capital or not, squared over AR. Here, R vector, from the point charge to this point, if you do, I'm doing Cartesian here, if you take a look at the difference in X coordinates, it's irrelevant. You follow me on that, class? because this is at x equals 0, and the point of observation is at x equals 0, so there's no difference. For the y coordinate, it's 0 minus 1, right? So it's minus ay. And then for the z coordinate, what is it? Just take a look. Coordinate point of observation is 2 minus 0, or just 2az. Same magnitude as the row vector. So our magnitude is simply square root of 5, correct? Then we can say E total, or E total at the point of observation, is going to be E row, which is rho L. And in my case, it's 2 times 10 to the minus 9 over 2 pi epsilon naught, which is 1 over 36 pi times 10 to the minus 9, over rho magnitude, which is square root of 5. Agreed, everyone? And then it's going to be times a rho. Well, a rho has a square root of 5 in it, so I'm just going to leave 5 under here. And then it's going to be times ay plus 2az. That's the first part. Then it's plus the second part, which is this. Well, q on this one is minus 5. So this is going to be minus 5 times 10 to the minus 9th over 4 pi, epsilon naught is 1 over 36 pi times 10 to the minus 9 over r squared, and r here is equal to square root of 5, r squared is 5. Then it's times ar, and ar here, I didn't put it, but ar would be equal to r vector over magnitude of r, which means this would be 5 to the 3 halves here, and then it's going to be times minus ay plus 2az. Do y'all get that, class? It's just sticking in the numbers. There's nothing tricky. The only reason I put 1 over 36 pi times 10 to the minus 9th is because the 10 to the minus 9ths cancel. That's it. So if I do that, this goes away. Right here. That goes away. Right there. Next, I try and manipulate this down as easy as I can. The 2's go away. Right there. Then the pi. Let's see, for this one, I get the pi goes away, and I have 4 over 36 is 1 over 9, or I can put 9 on top here, and 9 times 5 is 40. And then you just run the numbers, that's my point. So I can put 36 up top here, if you want. And you get an E total. Oh. Those quizzes there, I read the solution. Are these all the quizzes, or just yours?
Mine.
I don't have it, actually, I've got the solutions in my computer, but to forego that, do you have, I think you messed up one thing, right? What'd you get for the?
I've got 11.2.
AY?
Yeah. Plus.
Is that right? Did I mark that right?
Yes.
And for Z, you messed up.
I guess.
You did. I know. And for this one, let me just say this, if you run the numbers, because this is 40 over here, minus 40. I can give you the answer to this one, but this is for the AZ part. If you take 36 times 2, it's 72 by 5. Let me just put you what this is. So it's going to be 72 by 5. And then it's going to be minus 40 times 2 is minus 80. Minus 80 over 5 to the 3/2 power. Can you tell me what that is? It's small. I think he's got AY right though, that's the reason I'm not bothering. 72 over 5 minus 80 over 5 to the 3/2 power.
7.24.
I believe that's right. And you had like 0.2 something or point?
No,
What'd you
I
have?
had 6.35.
Is this 7.24 people?
That's what I got.
All right. I believe that's right. And I don't know how that happened. Anyway, and that's volts per meter. I wanted to do that. Please make sure you know how to do this. The point charge is usually self-evident, but that one wasn't. Are we good, class? Everybody? And again, I'll just encourage you to make sure you do the homework the day it's assigned or the next day at the very latest, because it will stay with you if you do it that way. You won't be overloaded. All right. Next. We covered, last time, we covered conductivity and its effect on resistance, and we went and calculated some resistances, and I asked you to do some homework. Were there any questions about the homework I gave you? No?
3.54.
All right. Now, I do supply solutions, and usually that eliminates a lot of questions. However, sometimes the solutions aren't as explicit in how they got the information. All right, this is 3.54? What is it?
A coaxial cable, inner radius A, outer radius B. And there's a voltage V applied to either end. Find the resistance per unit length.
All right, this one's not, the current's not flowing from the inner and outer. What they say is it's gotta have a length, right?
Yes.
What's the length?
It's
Arbitrary.
resistance per unit length.
All right. So we'll put a length L here, and here's the deal. The actual vault, or the thing that has material in it, is between A and B. So think of a long cylinder and core it like a pineapple. So they want the resistance between this end and that end here, right here. And they put a battery. I always like drawing visuals like this. Assume that this surface is metallized, that surface is metallized. So the way you do this is you're going to assume a current I. That's your first step. Once I have I, now I get the current density. And you have to realize that, we'll call this the Z direction, all the current is flowing in the direction from one of these planar surfaces to the other. Can you all imagine it? Just assume you take something that, take a solid cylinder and core out the center, get rid of it. And then all the current flows down the cylinder. It's going to be in the Z direction. And we're assuming the current density is uniform because there's no reason not to. We're assuming a certain conductivity in here, a certain sigma. So that means I is really, now we're going to get J, and J is going to be equal to I over the cross-sectional area in the AZ direction. Well, I is a constant. The cross-sectional area would be pi times B squared minus A squared in the AZ direction. Does everybody agree with that? The cross-section of just a circle, or a cylinder, is just pi A squared. But if you have a core out of it, then it's the outer radius squared minus the inner radius squared times pi. After that, I can say that E is equal to J over sigma, and that's I over pi times B squared minus A squared sigma AZ. And what's the last step? That's the E field. What do we need to get resistance? And how do we get voltage? Right, just integrate E dot dl. These are easy ones because the E field doesn't change in magnitude, right? So you're really just multiplying the E field, right, by the length to get the voltage. And the voltage here is strictly positive because resistance is always going to be positive. You don't even worry about the sign here. So you're just going from 0 to L of E dot dl. All that's a constant. dl is in the Z direction. If I wanted to be formal about it, I would say it's I over pi B squared minus A squared AZ, then dot DZ AZ. And I would go from 0 to L, and I can see now that I have my voltage equal to IL over pi B squared minus A squared Y'all agree with me there? To get resistance, if I've got voltage, I started by an assumption of current. To get resistance, what do I do? Just V by I is R, right? So I'd say R is equal to V by I, and that's equal to L. Oh, and that's times sigma, by the way. It's L over pi, B squared minus A squared sigma. Now, I told you this before, that anytime you think of the resistance of some long rod, it doesn't matter the cross-sectional area looks like. It could be a rectangular, it could be a circular, it could be elliptical, it could be triangular, hexagonal, doesn't matter. The only thing you worry about is the area that actually exists that the current's flowing through. And the general formula for resistance for any long rod of constant cross-section with a given conductivity, it's the length over sigma divided by the cross-sectional area. So that's cross-sectional area. Okay. Is there anything else in that one?
The answer solution has a log in it.
Well, then they don't want it between the ends. They want it between the inner and outer surface, though. Just read the, can you read that to me?
Determine an expression for the power dissipated per unit length, well, and resistance, in coaxial cable of inner radius A, outer radius B, and conductivity between the conductors sigma, if a potential difference of VAB is applied.
This one, they should have provided a picture. I don't think they did.
No.
This is the bad part. This is the way to do it if you assume the current flows down the z-axis. And I will show you a picture of these things when I ask you for information. What he is doing is this. He's saying, if I have an inner radius A and an outer radius B, I'm going to go ahead and put a plus voltage here, which will cause a current density to flow radially outward. Now follow me on this. To radius B. Does that make sense? There's a current he's going to put in the surface. Now, he's only going to take 1 meter of this. So it's a 1 meter long conductor. And we're going to put current into the surface and it's going to flow out radially. Can you envision this, everyone? So we do it this way. We start with I. And now we get J. Please pay attention to this part. J is always going to be the total amount I. We're assuming this thing has a 1 meter length. So it's like this. And all the current is flowing from the inner to the outer conductor. So that means now it's flowing through a cylinder shell of radius rho. Does that make sense to everybody? I'm sorry, I missed.
That's fine.
When I heard that, I'm thinking that.
I didn't understand what it was asking for.
And the way I set that problem up, it's correct. But this one's different. Now, it's the area that's this current density's flowing through. You all see the current densities flowing from the inner to the outer or in the radial direction, right? My surface is going to be a concentric cylinder at a constant distance rho that the current density penetrates, right? Well, that surface of a cylinder is always the length of the cylinder, all right, times the circumference. So the circumference is 2 pi rho times length. That would be the area of a cylinder of radius rho of length L. Does that make sense? We'll put in the dimension L. Now I have to divide, I'm going to say that is J. Well, what is J? Well, J is sigma E. I think everybody agrees with me, correct? So I can get E would be equal to I over 2 pi rho L divided by sigma, and it would be in the A rho direction. I should have put A rho here. And does everybody agree with me there? And then finally, once we have E, we need to get resistance? Voltage. We assumed I, right? From I we get J, from J we get E, once we have E we get V. So now we say voltage is equal to the integral from the inner to the outer radius of I over 2 pi rho L sigma A rho. And what is D rho for this case? When we go radially away, do you remember? Remember what DL was? I'll just put this up here. It's cylindrical coordinates, different than Cartesian. DL is equal to D rho A rho plus rho times D phi A phi plus DZ AZ. Now you'll notice when I take this and dot product it with D rho, the only thing that survives is D rho A rho. So I don't even write these other two terms. I know they're going away. So I just put D rho A rho. And when I do that, you can see A rho dot A rho is 1. I have I over 2 pi L sigma. Then I have an integral of 1 over rho d rho, which is the natural log of rho between B and A. I have a comment here. You'll notice I didn't put a negative sign there and go from B to A. Y'all notice that? I just wrote it this way, and I'm going to tell you, the reason I can be casual or sloppy is because I know that voltage is positive. I know that. So for whatever reason, suppose I had A over B, which would make it a negative voltage. I just flip that, make it B over A. Understand, everyone? That's equal to the voltage, and what's the resistance? V over I, correct? Therefore, if I look at that, it's what? 1 over, and if we let L be 1, because it's per meter, it would be 1 over 2 pi sigma times the natural log of B over A would be the resistance. Does he have that?
Yes.
Okay. That's how you get resistance. He also asked for power dissipated.
Mm-hmm.
I'm going to get to a different way to do it, but once we have resistance, what is DC power? If you have DC current, what is the power dissipated? Let me put it right here. Power, if you have a resistor and you have 1 amp going into it, and the resistance is 10 ohms, how much power? 10. I squared R, right? I squared, 1 squared is 1, times 10 is 10 watts. Really what you're doing is simple things, right? Well, power is always going to be I squared R. Now, does he assume current or voltage?
Voltage.
All right. Then if it's voltage, it's V squared over R, isn't it, class? So it's just going to be V squared over R, and if you take a look at this, would be the log of B over A, right? And this would be 2 pi sigma. And does he have that down there? So that would be the power, and I'm going to show you another way to do this in a second. Are you with me? And what I'm talking about here is just basic circuits right here. If you have a resistance and you have a voltage or a current, you can calculate power. Now remember, this is DC, or steady state, a constant current or voltage. If it was AC, there would be a 1/2 in front of that. Remember that, because we always use the peak value, not the RMS value for AC voltages. Okay. Now, getting back to what I wanted to show you. Is there another question about the homework before I continue? You got one? You understand all of them? Because I gave you problems with cylinders and spheres, right? And planes. I want the resistance between them. You should be very familiar with how to do that. And also be careful of one thing. This conductivity doesn't have to be a constant. And if the conductivity is a function of position, listen, then that means this E field is not going to be just 1 over rho, right? It would be 1 over rho divided by whatever the functional form of sigma was. So it wouldn't be just 1 over rho, which means that the voltage wouldn't have this log form in general. It could have any other form. So you can't memorize these things generally. I know it's attractive to do that, but almost guaranteed on my tests, I make sigma a function of position. Almost guaranteed. Got me on that? All right. Now, I'm going to do one more. No, I'm going to wait. I'm going to wait on that one until we get into the Poisson equation solution. I was going to show you one where I have half of this with 1 sigma, half of it with another. And there you have to assume voltage. You can't assume current. It's different. All right, and that's, but I'm going to wait until I get into Poisson's equation for that one. It'll make a little more sense to it. once we get a handle on Poisson. So today, what we're going to do is first talk about something called the power density. Now, you know what power is. It's either I times V back in circuits, or it's I squared R, or it's V squared over R. That's your power fault parameter, right? When we talk about power density, please write this down. Power density. We could use a lot of different symbols. I'm just going to call it P sub D. It's power, it's density. Small p, small d, density. Well, power density this is for DC currents, by the way, DC only. This is not for AC. Power density is equal to either E dot J, or it's equal to sigma times magnitude of E squared, or magnitude of J squared over sigma, and the units are watts per meter cubed. Now, think about a power density. A power is in watts. A density is always going to be meter cubed volumetrically, correct, class? So how did I get this? Well, this is the fundamental, E times J. When I look at E, the units are volts per meter. J is amps per meter squared. A volt times an amp is a watt. And if I have 1 over meter squared times 1 over meters, I get 1 over meter cubed. The units themselves signal it. There's other ways to do this, but this is the easiest to see it. So that's power density. Now, if you wanted the total amount of power consumed in a region, well, we can do that problem we just talked about, all right? We did this. We said when we had a cylinder, inner radius A, outer radius B, we take 1 meter long piece of it, and now we're talking about current flowing from the inner surface to the outer surface, right? And J, and we started by saying we're going to have a battery kind of deal, hook it up to this thing. This length is 1. Now we do this. We assume I. Now we get J, and J is simply going to be I over, and that's going to be this cylindrical surface when I'm out a distance rho. I put it in there. And the cylindrical surface is going to be 2 pi rho. That's the perimeter, right? Times the length, and we're going to let the length be 1, so we don't even put it in. That's J, right? Now, power density is J squared over sigma, right? So without doing the E calculation, now I can get the power density, and I know that's magnitude of J squared divided by sigma. Power density is not a vector, it's a scalar. So that would be what? It would be I over 2 pi squared divided by 1 over rho squared. Agreed? And the units would be watts per meter squared, correct, class? Everybody see this? Now, once I have the power density, how do I get the total power? Total power, not multiply, integrate through. That's real important. Well, that's a power density, it's a function of rho, see that? So now you have to do the integration. So now we're going to say power density would be equal to the integral, power, of the power density over the volume. Well, that's a triple integral. So first you put in your power density, which is I over 2 pi squared times 1 over rho squared. That's power density. Now we need a differential. Yep.
Where did the sigma go in the power density?
It should have gone there. It didn't, sorry.
Okay.
It should have gone here too. It should actually go right here, pardon me, not there. It should be squared. It should be right here. That's my bad.
Why is it squared?
Well, I'm sorry. Oh, my bad. Again, my bad. Here's what I should say. This is equal to J squared. Well, J is this. So if I square that, I get I over 2 pi, and I square that. I'm breaking the 1 over rho squared out by itself. So that's J squared. And then I divide it by sigma. Agreed, everyone? Sorry about that. And thank you. So this actually is right, and there should be a sigma here, and that's J squared divided by sigma, the power density. Now I have to multiply by the differential unit of volume in cylindrical coordinates. And what is that? Think about the differentials. It's d rho, right? It's, what's the next one? Rho d phi and dz, all right? Now, rho goes from where to where? From A to B. Phi goes from?
0 to 2 pi.
Right. And z?
0 to h or
0 to 1. As a matter of fact, for dz, since it's 0 to 1, we can ignore that part of the integration. If dz is integrated, it gets z from 0 to 1 is 1. So I don't even need to put that up because it's per meter. So what happens here, what I always tell people, I do this, is try to bring all the constants in front of your integration. So I have an I over 2 pi squared here, and then I have 1 over sigma here. Next thing I do is look and see how I can simplify the inside part of that integral, and I have a rho up top and a rho squared at the bottom, so it makes it 1 over rho. Now I put down the 0 to 2 pi, and the A to B here, and I have d rho over rho times d phi. Does everybody agree with that? I'm not trying to fly through this, but I'm just trying to make sure. If you've looked at this, this should be answering any questions you have. Y'all see this right here? You agree with me? Okay. You're looking at that hard.
Yeah, what happened, are we getting rid of the third integral?
Well, remember that's dz, right? It goes from 0 to
So
1.
it doesn't change?
From 0 to 1 is, the
One.
dz is just 1, so I ignored that. Now, what is this going to be? Well, the I over 2 pi squared is here, right? I have 1 over sigma, that's still fine. When I integrate d phi from 0 to 2 pi, I get 2 pi. Then when I integrate 1 over rho from A to B, I get natural log of B over A, correct? And here is the next part. Remember, we're calculating resistance using the power density. We got the power density just by J squared over sigma. Well, what is power in a resistor always equal to in terms of I? I squared R, correct? Isn't that right? So if I look here, can you see the I squareds cancel? And what's left is the resistance. So I'm going to go ahead, do y'all see that? I'm going to get rid of the I squareds. And when I look at this, watch what happens. I get 1 over 2 pi squared times 2 pi. I get rid of that 2 pi, right? And now I have this. And that's what we had last time. And here I used power density to get that. Yep.
Oh. Never mind, I see what you did, I'm sorry.
The only thing I try to do is simplify it down. And that's using power density. Now, power density is real important for a lot of calculations. And let me just tell you my experience where it became very important. By 97, 98, 1997, 1998, I was working for Avon Air Force Base. And what we were doing was modeling metals under the action of large currents. Really, these are detonators. Well, what happens to metal, or anything basically, it goes from a solid to a liquid to a gas as it's heated. And if you put a very large current density in there, it goes fast. Now you need what's called a specific heat, and then you need the coefficients. You have to have the resistivity of the metal as a function of temperature, and there's a lot of other complicated things. But we used a finite element program to estimate the actual shape really it's the thermal, it's a 3D picture of the time evolution of the pressure wave that would come from a piece of aluminum that's heated. And I can't get into the exact shape because this is a detonator. But what we did is we modeled the aluminum foil using really just the fundamental laws. That J is sigma E, and E is minus the gradient of the potential minus the ADT. You'll see that this comes in later when it's time varying. So we use Maxwell's equations. We use the equations for materials of sigma that talked about how they change state. In other words, we use specific heat and everything like that. We use something called the Navier-Stokes equation. Are you familiar with this? Navier-Stokes has to do with fluid flow. All right, there's compressible and non-compressible fluid flow. And then we also, well, those two equations, and we use the basically the equivalent of PV equals nRT, Boyle's law, but it's a variation of that that's sort of embedded in this. And in the simulations, not going through everything, but we showed how it would actually behave. And it wasn't a real detailed analysis because there's certain things you can't describe very well when you're modeling. For instance, surface imperfections play a role in how things blow up and all this stuff. But it gave a very good idea of the way things would happen. And indeed they did that way. Now the power density, when we did the modeling in the aluminum, was the key, because that power density tells how much power is being deposited per second, or in some senses per really millisecond, microsecond, picosecond. That power density it's deposited goes into heat, so it increases the heat. Now there comes a point, you know what the specific heat is? Remember that in chemistry? Well, you know how when you go from water from liquid to ice, or from ice to liquid, it takes a whole lot more energy to go that 1 degree in either direction. Well, with metals, it takes a whole lot more energy to go from a solid to a liquid, and then from a liquid to a gas. So you have to include the specific heat involved in that. So when you're doing power density, it's not going to just go up in temperature and keep going. What it does is go up, stop in time, because it's got to heat up to a point where now it can go to its next phase, molten. Then it heats up some more, and then it stops and lays constant until the specific heat requirements are required. That much more heat's put in, and then it goes to gas. And then once it goes to gas, it's over, because now you've got a pressure wave. So we modeled that and it was very accurate. And again, one of the things became very important in the modeling was the power density in the metal. So I want to tell you that that's real and it works. And I've used that in other places too. It's something you have to know, especially nowadays when there's so many things that are done at microscopic, really of dimensions of microns or less, where they put very large current densities into regions for only a second, but they want to make sure there's not a failure, because here's what happens with a lot of devices. Most of the time when you think of electrical engineering, how a thing fails, you think about something arcing through like a silicon dioxide, a dielectric. That's how MOSFETs fail all the time. But it's not just that. When you have single thin wires that all of a sudden experience a fairly large current, just for instance, say with lightning hits, it induces a voltage, it induces a current. That current, even though it's only there for a millisecond or less, may be enough current to heat that wire to a point that it melts like a fuse. And you have to be aware of how to model that if you're in the real world, if you're asked to do so. Because a lot of this stuff, there's no handbook, you can look this up for a lot of things that are coming out. Things are coming out so fast these days, there's so much innovation, that when products go into the field, usually that's the real test. They find failures, and I can tell you a story about a company in Huntsville that fielded like 10,000 cards that are worth a lot of money each card, and they start failing left and right with lightning. Well, they thought they did a compliance test, but again, their device had different dimensions, different wires, all the compliance, the way they usually tested a product, wasn't valid for the product they created. So even though it passed their test, it really didn't pass the test in the field. And they got in a lot of trouble for that. I got involved in that, and I just know bits about the problem, but if they could have modeled the products better and then put it in a true environment, it would have given them a much better idea of what was going to happen. There's something that they do a lot of times. This is from my work at the Army. Now, they don't simulate the electric fields created by, they don't simulate real lightning. They can't. Lightning's huge, right? You gotta be up a couple of miles to create this. So what they do is they get a scaled model of lightning, and then they basically scale it up to what a real lightning event would cause in terms of current density on stuff. So we were doing a test. I'll tell you this real quick. In 1990, we were working on a multiple launch rocket system right before the Gulf War. It's just a bunch of tubes with rockets. And don't worry, with missiles, and don't worry about what's in them, because it doesn't matter. I didn't care. They wanted to know the surface currents on these tubes. So the lightning would cause, because they wanted to see if it would cause an ignition of one of these missiles. And that's really important, because if that happens with lightning nearby, then a lot of bad things can happen. And especially when you're shipping these things, by the way. There's lightning all over Florida, there's lightning all over the East Coast, and it was the summertime, and things can go wrong in a hurry. So what they have is if anybody's seen this, let me know. They have a grid of wire. It looks like a fence, just a fenced region about 20 or 30 feet high. Maybe it's actually higher than that. It's about 40 or 50 feet. And then they have the ground with a whole bunch of wire on it. And those look like two plates of a capacitor. And what they do is charge, they're called a Marks-Bank generator. They have very large voltages, and they charge this enormous set of capacitors to millions of volts, and they put it on the top, that giant, so it's a giant electric fence on top, but it's planar. And then they put the thing under test under it, which would be the multiple launch rockets. And this is with nothing in them, and it's inert. And the tubes are basically, they have metal braces and stuff, but they're fiber, and you don't have to worry about that. So the way they initiate a lightning striker at a point, they take a little paper clip, and they tape it on and bend up the end, and that looks like what's called a hot point. It's a field emission point. It's where lightning will hit, or that discharge will hit every single time. So then they put their current probes, they're called B-dot probes, all around, and they just measure how fast the current changes. They get the current signature. B-dot probes use fiber optic outputs, because if it was metal, coax works horribly in the proximity of a lightning event. They can't use anything that could be influenced by the current that caused EMI. So they have B-dot probes, they have fiber optic out. So I was watching, they charge it up and bam, hits. And they get hundreds of kiloamps of current. Real lightning, actually not hundreds, 50 kiloamps of current. Real lightning can go up to about 270 kiloamps, but that's extremely rare. Those are called superbolts. Most of the time it's about between 20 and 50 kiloamps peak current with a certain duration. Well, they can get the current coming up fast enough, but real lightning has a much longer duration than their events. So what they do is they use a scaling process to estimate the actual electromagnetic signatures and current density on the missile in time. And that works great for a lot of things, but some things it doesn't work great for. And one of them was a nuclear missile called the Minuteman missile years and years ago in Europe, because one thing they didn't do in the modeling, they didn't account for both the lightning's duration. Actually, this is a little different. I gotta be careful about this one. They didn't account for certain things. It wasn't just lightning, it had to do with electrostatics. And a Minuteman missile, when it was being shipped, and it was actually being loaded, it was very cold, it actually ignited. And that's a nuclear tipped missile. And that caused a whole lot of concern, because that could have been, think about it, what happens if a nuclear weapon is launched and goes off in Czechoslovakia or Russia? Who knows? It's a wild card, but that was the kind of scenario, and then they put everybody on it. And a guy from here named Dave Nauer is the guy who fixed that problem. He was in his PhD work, and he was working there, and he solved the problem. Anyway, it all boiled down to one thing. His understanding of fundamental electromagnetics and material science, and understanding how a simple scaling, trying to scale up things doesn't always work. I'm just telling you that as a story. I'm supposed to give you some real world information. That's my real world information about how power density and really scaling doesn't always work so well. Oh, power density does if you do it the modeling correct, but scaling doesn't. All right, now the next thing I'm going to talk about is, first, any other questions about resistance and power density? I could go on about power density, but it's really just use the equation, do the integration. Next thing I'm going to talk about is really going to be something called the electric susceptibility. And this is now in dielectrics, so write this down, and I'm not going to try to just give you a lot of abstract knowledge. I'll try to get right to the heart of the matter. So these are dielectrics. And when we talk about dielectrics, these are really insulators. Like rubber, mica, quartz, things of that nature, plastics that prevent any kind of current flow. They really electrically isolate things. But when we talk about dielectrics, we have to understand certain things about it. When you have a dielectric, you have basically this, and I'm going to try to be as simple as I can. You have a plus and minus charge centers to molecules that are bound within a dielectric. You know how water has, H2O has a positive, negative charge center? It's always true. Well, dielectrics, water is something that is a bit, DI water is a dielectric, but I like to think of a solid when I talk about this. Now, I've oriented these things in this direction. They don't have to be in that direction. Some of them could be here, but I'm showing the charge centers. Now, when I put an electric field in this direction, what happens is there's a force, electric force on the positive and an electric force on the negative in opposite directions. These charge centers actually have a little like spring, an electrical spring in there. If you think about charge centers, there's something in holding them in the position they're in. If they try to stretch away, there's a force that'll pull them back, and if you try to compress them, there's a force that'll push away. It's like a spring, it's an electrical spring. Well, when you put an electrical field in there, it stretches this a little. Does that make sense to everybody? And these are the molecules. When it stretches the molecules, those molecules store energy. So a dielectric has some ability to store energy more than a vacuum would. And that's where they use the term the electric there's two terms actually. There's a dielectric constant and the electric susceptibility. So first, and polarization. So they use the term polarization, capital P is polarization. And P is given as simply the electric susceptibility times epsilon naught times E. And here, this is the electric susceptibility. We don't use this much. This just gives it's a figure of merit of how much polarization is going to be impacting the D field, and you'll see this in a second. Now, they define the D field, and remember, D is really, that's in coulombs per meter. The D field is going to be equal to really P plus epsilon naught E, or it's equal to chi S epsilon naught E plus epsilon naught E, or it's equal to 1 plus chi S electric susceptibility times epsilon naught times E is D. And I'm going to just say one thing. If you get into material science and materials engineering aspects, then this becomes much more important than I'm making it out to be. Right now, I'm just giving you, I'm basically giving you a clue into things that are important. I'm not saying how we're going to use it. This is what we're going to use. You see how once we add P plus epsilon naught E, we get D. That's P, that's D is epsilon naught E in free space. Then we get 1 plus chi S times epsilon naught. And this is the important one right here. Now we say D is equal to something called epsilon R, epsilon naught times E, and epsilon R is 1 plus the electric susceptibility. And this is given the term dielectric, relative dielectric constant. And what that is something, it's a figure of merit on how much better the dielectric can store energy than free space can. Now, a dielectric constant, epsilon relative, is typically between about 1, it's greater than or equal to 1, and less than about 50,000. I'm gonna tell you, there's probably materials out there that it's greater than 50,000 for, and I'm just throwing that number out. Typical dielectrics that you and I deal with in non-exotic materials, 1 to about 10 at the most. Now, there are examples. Water, for instance, has a salt water, fresh water too in some cases, has a dielectric constant of about 81. That's high. But most don't. If you think about quartz, mica, things like that, somewhere between 2 to 4.4, good insulators. Rarely do you get above 6. If you look in the back of your book, if you have a book, if anybody does, if you go to the back, it's going to have dielectric constants back there, at the very back. I'm just trying to give you an idea. He actually probably has values in chapter 2. Is this epsilon on?
Yeah, it says epsilon T, or R, this is R.
Well, if you look at these values on page 625, he's got it at 1.005 for air. It's about 1. If you look at alumina, it's 8.9. If you look at barium titanate, it's 1200. That's rare. Glass is 10. Where's water in there? Seawater, 72. Actually, fresh water is about 81. Ah, there you go, 81 distilled water. So you see the range, 1200 is extreme. That's a complicated material. Most of the time you're about 1 to 10. Just keep that in mind. And for most practical insulators, 3 to 5. All right, those are the ones that we use every day for insulation. So that's sort of how epsilon relative impacts the actual value of D. And this is the equation that you worry about right here. And generally speaking, we just say that D is equal to epsilon times E, but epsilon is assumed to be epsilon relative times epsilon naught. Another thing I'm going to say, even though we're at DC, epsilon relative is a function of frequency, but that comes later. So at high frequencies, the value of epsilon relative changes. And I'll tell you where it's most pronounced. If you look at water, at optical frequencies, you can see a long way in seawater, right? Well, you're going to see that's because epsilon relative for that, the loss factor that you'll see later, is very, very low at optical frequencies. But if you get down to frequencies that we communicate at, like gigahertz frequencies, then the conductivity as well as the value of epsilon is much, much, much higher, and it quenches the signal. It doesn't go very deep. That comes later, but it gives you some perspective. Now, after I do that, where we're going with this is capacitance. We've done resistance, now we're going to get to capacitance. But before I do that, I have to go through some boundary conditions. So there's 2 big boundary conditions in electrostatics you have to worry about. And they're related to the tangent and normal field. I don't like spending a whole lot of time on this. I like to, because you've had some of this before, I like to show you how come it's the case. And just listen to me. You don't have to write this, just listen. Let's assume I have a planar surface here, and I have one material here, and a different material here. And I'm just putting this down to show you it's a different material. Now, when I have an electric field, suppose I somehow I immerse this thing in an electric field, and I'll just say without this material, it has a certain orientation. I put the material in the region, it's got an electric field that was already present, and what might happen is the electric field here might be this way, and the electric field here might be this way. They'll be constant everywhere in this material. E2 will have that magnitude and orientation. E1 will have that magnitude and orientation. Does that make sense to everybody? It's hard to get a grasp of, but here's what really I'm saying. Let's assume that I have an electric field that looks like that everywhere when no material is present. Now I introduce a material, and for now, don't worry about the extent, assume it's infinite. Where above the region it has some epsilon 1, below epsilon 2, 2 different regions with 2 different epsilons. This is epsilon 1, epsilon 2. When I look at this, I'm going to make the case that the tangent E field across both boundaries has to be the same. And here's how they do it. They put a small little mental, this is just an abstract construct of the mind, a box there. And they say, well, if I take a look at the electric field here, if this is the tangent electric field in region 1, and that's just a projection of this field in the horizontal plane, here, let's assume that this box has a length L and it has a height H and it's centered, right, so that half of it is above, half of it below that plane. And down here, there would also be an electric field, right? And that would be E tan 2. That would be the projection of this vector into this plane, the horizontal projection. Don't worry about all the details. Now, here's the thing. If I integrate the E field over any closed loop, this is a loop, dot dl, I get 0 for electrostatics, and let me show you why. You know that the E field is equal to minus the gradient of the potential V, correct? Well, if I integrate minus the gradient of V dot dl over any closed loop, that's the same thing, and this is Stokes' law over a closed loop, as integrating minus, actually it's the divergence of minus, sorry, it's equal to integrating the curl of minus the gradient of the potential V over the surface that this loop would actually encircle. In other words, if you're going around a closed loop like this and you're integrating the integral of minus grad dl around that loop, it's the same thing as integrating the curl of grad V over that surface. Does this make sense? Please realize the mathematics sometimes obscures the simplicity of this, but I'm just trying to make a point. Now, the curl of a gradient is by definition 0. And that means this is 0. And here's really what I'm saying. If you have 2 points, A and B, and I have a meter, and I put the plus lead here, and I put the minus lead here, I can measure a voltage between those, right? But if I start here, end up here, when I do the integral of E dot dl around any point, I would get the voltage between A and B. Do you agree with me? Well, what about A going to A? What if A becomes A? If I start at A and I go all the way around and I put my meter, the B lead right here, how much voltage do I measure? 0. Well, that's what this is. If you literally take your meter leads and put them at the same point, where you start and finish, you measure 0 voltage, and that should make sense. That means if I integrate E dot dl around that loop, I get 0, correct? Does that make sense? So if you let H go to 0 here, then the integral of E dot dl around that loop, the integral of E dot dl for this little region would really be the tangent field in region 1 times whatever that length is, minus the tangent field in region 2 times that length. And that should make sense. If I start here and I go around and H is insignificant, I get E, the tangent electric field in region 1 times L, but then when I go this way, E field's that way, dl, this is that way, I get minus L times E tan 2. Follow me? And then the bottom line on this one is E tan 1 is equal to E tan 2. It means the tangent electric field on one side of the boundary, just below it, is exactly equal to the tangent electric field right above it, and it has to be. All right? So E tan 1 is E tan 2 because there can't be a difference, or when you did a simple closed loop integration, you would get non-zero voltages at the same points of the leads. Would you follow me on this, class? Now that's the tangent electric field. E tan 1 is E tan 2. Remember that always. The next has to do with the normal D field between 2 regions. So if you have a region 1 and a region 2, and here you can assume this has epsilon 1 and this has epsilon 2, then what they usually do is this. They say the way to actually see what I'm about to tell you is, suppose we have a little pill box. And we're going to have half of the pill box above it, half of the pill box below it. And we got, assume that we go ahead and we have a charge density rho s on the surface. It's not a very good pill box, but I could build a bigger one. I'm not sure it's really gonna do much good. We can put the surface here, and we can really say now, if this has a charge density rho s, there's some D field in region 1 here, and there would be some D field in region 2 here. Now, that's actually the normal D field, so I'll call it just D normal in region 1 and D normal in region 2. The reason I'm showing only the normal is because I'm going to take and use Gauss's law here, and I'm going to say that the integral of D dot ds is equal to the charge enclosed, which is the integral really of rho s ds over the surface. And really that's just going to be, if this is a radius a, then the amount of charge in there would be rho s times a. So work with me on this one. Here's what I'm about to do. I'm going to shrink the height of this box and let the height go to 0. So I'm going to squeeze it down so I'm just at the surface, just above and just below the surface. And I'm going to say that the integral of d dot ds is going to be equal to the charge in that surface times the area, charge density times the area. So when this happens in the limit, as h goes to 0, now I'm going to get d normal 1 times the area, and I'm going to have that minus d normal 2 times the area. D normal 2 is equal to rho s times the area. And really, I want you to write this down here, because there's two things that are important. Write this down. If, and only if rho s, the surface charge density, is 0, then d normal 1 is equal to d normal 2. That has to be the case, because if rho s is 0, then d normal 1 has to be d normal 2 in order for this to be 0. So the D field, if rho s is 0, d normal 1 is equal to d normal 2. Now the second thing I'm going to show you takes a little, it's a little hard to understand, but it helps if you're worried about it. If you have a vector, he calls it A21. A21 is a vector that starts in region, actually, I got this drawn wrong. Let me just see your book for a second. No, I have it the way he's drawn it. This is on page 188. That's 2, or that's 1, that's 2. A21 is a vector that starts here 2 and goes to 1. This is A21. He's got, it bugs me a little. The normal direction goes from medium 2 to medium 1. A21 is a unit vector from medium 2 to region 1. I don't like that because usually a vector starts here and ends here. But here he's calling A21 a vector that goes from region 2 to region 1. Follow me? I don't like that. It should be A12, but he's got it this way, just accept it. Really what it is, it's a normal vector that's in the vertical direction, and you always stack it 1, 2. Well, if you have that, then if you take A21, just write this down, that's that unit vector, and you take it and you dot it into D in region 1 minus D in region 2, and he hopefully has that. Yeah, he's got that right. Is equal to the charge density. Now, what he's doing there, this is basically the point form of this law. If you look at this, right, when I would be doing this, the actual surface vector, ds here on the top part, is in the positive direction. The surface vector for this part that I show you here, or when you integrate ds over the bottom, would be this way. All right? And what effectively that does with that dot product is taking the surface vector here and using that as the normal. And whenever you have a normal and you dot it into these vectors, it only extracts the normal component. The other components that are horizontal, that aren't parallel to it, are zero. So this is really d normal 1 minus d normal 2 is equal to rho s. That's the way I do it. I just say d normal in region 1 minus d normal in region 2 is equal to rho s, and I'll be done with it. But this is the formal way. Okay. I'll give you problems with that, but here's what always happens when you have these problems. If you're given an electric field in one region and you want the electric field in the other, you break this up into the tangent electric field. You know that electric field tangent in 1 is tangent in 2. And then you take the normal component of the D field here. Now, if the normal component, if there is no charge density, the normal component of the D field here is the D field here, the normal component. And then you can get the electric field by taking that D field and dividing by epsilon. Do you follow me on that, class? That's the way these problems are done. I have 12 after. Is that right? Okay, good. What I'd like to do, I didn't get the capacitance, but what I'd like to do is go ahead then and do a simple problem that's in the book on this. These get a little irritating, by the way. If I look in the back of the chapter, when it has dielectrics and boundary conditions, can you read me, or anybody read me 362? And I'll put it right here.
For y less than 0.
Okay. I'll put y this way. Y less than 0.
Epsilon R1 equals 4. And E1 equals 3ax plus 6 pi.
E in region 1 equals 3ax. Go ahead.
Yep, plus 6 pi ay plus 4az.
Okay.
And then it says at y equals 0, rho s equals 0.25 nanocoulombs. If sigma r.
0.25
Yeah, 0.25.
nanocoulombs per meter squared.
Mm-hmm.
All right, go ahead.
And it says if sigma r2 equals 5 for y greater than 0, find E2.
What for sigma?
Or
Epsilon.
Sorry.
Epsilon
R2 equals 5.
And this is in region 2, right? The whole idea is the y. Everything's with respect to y. So this is the y-axis. This is less than 0, greater than 0. Follow me? Now, call this region 1 and this region 2. First thing we do is get a unit vector in this direction, from 2 to 1. That is your A to 1. Well, that would be minus AY. Do you all agree with me there? Right. If it goes from 2 to 1, it's that way. Now we do this. He wants the E field in region 2, is that it?
Yeah, he says find E2.
All right, now take a look at this just for a second. That's the y direction, therefore x and z would be in the plane, or parallel, right? It would be in the plane of the floor. Take a look at this. If that's E1, what is the tangent component of that? Tangent, see, here's the surface definition. Everything above is one surface, below y. So what's tangent to that? Anything except the y component, right? So the tangent would be equal to this and this. These are E10 in both region 1, which is equal to E10 in region 2. So we've got these two as tangent, right? Agree, class? Y'all see this, what I'm talking about? Tangent means it's in the plane of separation. What is the perpendicular? That's the tangent. Wouldn't this be E perpendicular? That's E perpendicular, correct? So that's 6 pi AY. From that, I can get what? That's equal to E normal, right, in region 1, and therefore we can get D normal in region 1 would be what? Would be that 6 pi AY, right, divided by what, or multiplied by what? If that's E, how do we get D? Multiplied by epsilon relative, epsilon naught, right? So if we take this and we multiply it by epsilon relative, and region 1 is 4, epsilon naught, that would be D normal in region 1. Agreed? If you find the E field that's normal and you multiply it by the value of epsilon in that region, you got the D field, don't you? Now, that's D normal 1, right? You'll notice it's in the Y direction. Now we go here and we know that A21 times D normal in region 1 minus D normal in region 2 are equal to rho S, correct? All right, now we're just applying something. What is A21? Well, A21 is a vector that points from region 2 to region 1, which is minus AY, correct everyone? So minus AY, and then we've got D normal 1, which is 6 pi times 4 epsilon naught AY minus D normal in region 2. I'm going to just give you a clue here. The normal component in region 2 is in the Y direction. Do you all see that, class? So I'm just going to put D2, D normal 2 AY is equal to rho S. And rho S was 2 nanocoulombs, or 0.25 nanocoulombs per meter. Let me just finish this problem. So I just want to go through the math on this one. Rho S is up there. If I have AY, and this is a dot product, right? Sorry, dot product. AY dot AY is 1, right? But there's a minus sign, so this boils down to this. If I look at D normal 2, minus times minus is plus, I have D normal 2 here would be equal to rho S, whatever it is, plus this term, right? Plus, which would be 24 times pi epsilon naught. And that would be D normal 2, correct? Based on the formula. Do you agree with me, everyone? The only thing I did is 6 times 4 is going to be 24. Then I have epsilon naught, right? And that's a negative, so I take it to the other side, makes it a positive, and I'm left with D normal 2 on that side. Correct, class? The AY's dot each other out. Now when I look at that, if that's D normal 2, how do I get the electric field that's normal in region 2? In that region, right? So then I divide this by what? It's 5, right? Times epsilon naught, right? That's epsilon relative to, and that would be equal to epsilon naught times 5. This would be E normal in region 2, and it would be in the AY direction. So I'm just saying that that would be the normal. We have the tangent already. We have it's 3AX plus 4AZ. Therefore, now we'll have the normal. We add that on. And that would be the E field in region 2. I'm going to give you some problems to do. We'll see you on Wednesday. Thank you. Y'all understand what I was doing here? This is irritating though, this A21 designation. I don't like that at all. I just like the way I do it. D1 minus D2 normal is equal to rho S, and it's always D1 is the one in material model.